Good morning, everyone. So I'm Lenaik Shiza, will be one of the lecturers in this week. And for this morning, we'll have the pleasure to hear Laurent Massoulié, who is a researcher at INRIA in France. And he's also the director of Microsoft Research INRIA Joint Center. He's an expert and has done many contributions in unsupervised learning, in distributed machine learning, and also on the analysis and the design of algorithms on graphs and distributed systems. So Laurent Massoulié.
So it's a pleasure for me to be here. It's my very first time in India, so I'm enjoying it very much. So I'll be talking today about a problem that I've been working on for the last 4 years, a bit more, which is the topic of alignment of graphs. And tomorrow I might switch topics and tell you a little bit about distributed optimization problems. So let's get going. Right, I can get this to work. That is a quite famous problem in theoretical computer science, which is a problem of graph isomorphism, which is illustrated by the picture here. You are given two graphs on sets of vertices. They have the same numbers of vertices each. They have edges connecting their vertices. So you have G1 on the left, G2 on the right. And you're asking whether there exists a graph isomorphism between one graph and the other one. And the graph isomorphism is a bijection from the vertex set of G1 to the vertex set of G2 that preserves adjacency. So it sends an edge to an edge, a non-edge to a non-edge. And so it has puzzled computer scientists for a long time. They have many conjectures on this. They believe they know the problem is in the class NP, but they think it's not in P, and they think it's not NP complete either. So this would be one of those strange beasts in the class of NP problems, neither in P nor in NP. And so the alignment problem is quite related because this is the task of finding not an isomorphism between two graphs, but instead a near isomorphism. So formally, we ask for a mapping from one vertex set to the other vertex set. And we ask that this mapping preserves most of the adjacency structure. So here I've drawn the same two graphs, G1 and G2, except that I have removed an edge on the top right in G2. So you see now that B and D, so B and D here are sent to 5 and 7, and so it's an edge sent to a non-edge, but apart from that, the adjacency is preserved. So we have a near isomorphism between these two graphs. And so one way of formalizing the task of graph alignment is to say, I'll look for a mapping F from vertex set of G1 to vertex set of G2 that minimizes the numbers of disagreements between adjacency in the starting graph and adjacency in the end graph. So why would we care about solving this kind of problem? Okay, before I do that, let me rephrase it a little bit. You can reformulate this objective as maximizing the trace of a matrix, and the matrix, the trace of which you maximize, is a product of 4 matrices. You have A1, which is the adjacency matrix of graph 1. Pi is the adjacency, the matrix associated with a permutation over n vertices. So we assume we have the same number of vertices on both sides. So pi would capture the mapping you are considering. So A2 is the adjacency matrix of graph 2, and pi transpose is the permutation matrix associated with the reciprocal of the permutation associated with pi. So it's a simple exercise to see that what we're trying to do here is to maximize the trace of this program, of this matrix. So this kind of problem is called a quadratic assignment problem. And this is in contrast with a so-called linear assignment problem. So a linear assignment problem is when you have a series of vertices on the left from 1 to n, series of vertices on the right from 1 to n. You have a cost Cij of associating I to j, and you're asking for the matching from the vertices on the left to the vertices on the right that maximizes the sum of the rewards or minimizes the sum of the cost. So a linear assignment problem can be solved in polynomial time, whereas the quadratic assignment problem is known to be an NP-hard problem. So in this sense, we know a little bit more about the computational hardness of solving this task than what we know about the graph isomorphism problem I was mentioning first. Okay, so that's the kind of objective we are going to look into. Let me say a few words about applications now. So there's one application which is about de-anonymization of social network data. So you may have two data sets corresponding to two online social networks. You may have one where the identities of the individuals are revealed, and on the other one, they are hidden. This is an anonymized data set. Now, if you are able to associate the anonymized identities with the revealed identities in the two graphs, then you have de-anonymized the data set. So this is something that, that has been done, actually. I think one of the seminal papers trying to do this de-anonymization of social network data was in 2008. There was a very nice paper by two guys, Narayanan and Shmatikov, I believe. So what they did was the following. There was at that time a Netflix prize. Netflix had disclosed the data set with anonymized Netflix users, movies, arrows between users and movies. And they said, Netflix said it's perfectly fine to disclose this data set. It's private because we have removed the identities. Now, Shmatikov and Narayanan took this. They took a data set, which is the movie lens data set, where you have users rating movies, but they disclose their identities. So Shmatikov and Narayanan came up with an algorithm, and they said we can de-anonymize the Netflix data set using our algorithm. So, but they did not reveal the disclosure. On the other hand, another guy in Russia said, okay, let me run the algorithm. Here are the de-anonymized identities. He put it online, and so Netflix stopped launching prizes with those kinds of data sets because they figured out they did not quite understand what it meant to sanitize the data set and make it privacy compliant. So that's one kind of application that you might have. Exactly, yes, it was different. You had bipartite structure, movies and users. The numbers of nodes of one kind or another were not the same. You can still try to align if the two vertex sets have different sizes. I will not consider that today, but you can definitely do that, yes. So that's one first application. Let me mention one that is quite different that people in medical imaging consider. So in medical imaging, in the study of brains, people acquire automatically 3D images of the cortical surface, the outer surface of a brain. Then they automatically produce meshes. These are triangulations of points spanning the cortical surface. So what they want to do once they have acquired this triangulation of a cortical surface of a patient, they want to align it with a reference mesh of a brain that they have already annotated, where they have clustered the regions of the brains into the parietal lobe or whatnot, the Wernicke area. So you have all those things that have been considered and analyzed. So if you have your patient's brain and you align it with a reference brain, automatically you know which region corresponds to which cognitive tasks, and then you can figure out whether there are problems in one or the other. So third kind of application you might consider, which is a bit more far-fetched, but nevertheless, let me mention it. You could have two languages and then do some embedding of your words in your language into some high-dimensional Euclidean space. Now that you have these two embeddings of words into Euclidean spaces, you can create a graph, say nearest neighbor graph between the words embedded in your Euclidean space. And now, if you can, if you do an alignment of these two graphs, then maybe what you get is a poor man's bilingual dictionary, allowing you to go back and forth between the two languages. So I think for French, English, Hindi, English, this will not produce a state-of-the-art dictionary, but maybe in some languages for which you have less material, you don't have the reference dictionary already available, then this could be an approach to at least grasp some structure of a language you don't quite know. Okay, so many applications. So we feel justified to study the problem in the abstract, and we will study the problem in a very stylized framework where we will assume that the two graphs that we are trying to align, they come from a generative probabilistic model. And the probabilistic model we will be considering is an augmentation or a variation of the most famous model there is of a random graph, which is the celebrated Erdős-Rényi random graph model. So here you have Paul Erdős on the left and Alfred Rényi on the right, if you want to know. So I guess you have already heard about Erdős-Rényi random graph models. This is the simplest random graph model you could imagine. If you had to produce one, that's quite likely the one you would propose. It's specified by the number of vertices that will be n for us. And then it requires that edges be placed in the graph with some probability p, and you put an edge at one place independently of whether you put an edge at any other place. So it's really the simplest model of a random graph you can imagine. Now we want two graphs, not just one graph. So this is what we are going to describe now. So instead of one random graph, we'll have two random graphs, and we'll want them to be correlated in the study I'm going to explain. And so we do as follows in order to generate two Erdős-Rényi random graphs with parameters n for the number of vertices and p for the probability of an edge being present. We have a third parameter in our model, which is S, which is some correlation between the presence or absence of edges in the two graphs. And so the procedure is as follows. We start with a master graph, G0, which is an Erdős-Rényi graph on n vertices, and an edge is present with probability P over S, okay? And so we produce a first graph by downsampling the edges of G0. So we keep them with probability S independently of everything else. So that produces a first Erdős-Rényi graph G1, which obviously has parameters n and p. And so to produce a correlated version of that, then we start once more from G0. We downsample its edges with a probability S of keeping the edges. And we do this independently of what we have done for downsampling for G1. So that gives us G prime 2, okay? And you can work it out. The probability that an edge is in both, an edge ij is in both edge sets of G1 and G prime 2 is going to be PS. Probability that an edge is in E1, not in E prime 2 is P1 minus S. And so the statistics are quite straightforward. You can really write them down. And indeed, we have two correlated random graphs. Now, the game would be very easy if I revealed G1 and G prime 2 because I have not messed up the labels yet. So what I do last to have my observations in my task of aligning the graphs is that I will rename at random the vertices of G'2, and this is how I produce G2. So formally, I pick a permutation sigma star uniformly at random in the symmetric group with n elements. And the adjacency matrix of my second graph G2 will be A2, which is adjacency matrix of G'2 pre and post multiplied by a permutation matrix associated with the unknown sigma star. Okay, so with this setup, the game, when I want to align the two graphs, we will change it a little bit. Initially, I mentioned alignment is trying to find a mapping that preserves as much as possible the agreements between edges and non-edges. Here we have conveniently introduced in our model a notion of a ground truth because we generated the two graphs using permutation sigma star to mess up the labels. And so the ground truth that we would like to retrieve will be this sigma star. So the game is as follows. We get the two graphs and we would like to retrieve sigma star. Okay, so I will keep mentioning using these the following constructs. Given two graphs, G1, G'2, say on the same node set, I will consider the intersection graph is going to be the graph on the same node set whose edges are the pairs of vertices which have edges in both graphs. So that's G inter here. And so in our model, it's straightforward to see that we have again an Erdős-Rényi random graph. Now the probability of an edge being present is P times S. Okay, and I could also consider the union graph, which would be the graph on the same vertex set where an edge is present if there is either one or another type of edge between the two vertices. Okay, so as I said, what we will be looking for is a retrieval estimation of the unknown sigma star from the observations of the two graphs, G1 and G2. And so there has been work, as I said, starting in 2008 with the Narayanan and Shmatikov. They were motivated by de-anonymizing online social network data. Nice theoretical results started to come out on this problem in 2016. One important such result was obtained by Daniel Kulina and Negar Kiavash, and they characterized in this particular model when it is information theoretically feasible to recover the unknown sigma star. And the condition they have is that n times ps, which is essentially the average degree of a node in the intersection graph. When this is log n plus something diverging to infinity as n becomes large, then it is information theoretically feasible to recover sigma star. However, if this condition is not met, it is not possible. So it's a sharp if and only if characterization. And people then were interested in determining when it is feasible in polynomial time to recover this unknown sigma star. And results started to come out in 2018. There's been a rapid progress on the question. So the first results required the average degree n times p in both graphs G1 and G2 to be polylogarithmic, and that the correlation parameter S be close to 1, so 1 minus S be like the inverse of a polylog function. This has been improved. Recent work allows you to have the correlation parameter bounded away from 0, and we will see we have explicit conditions by now. There was work by Cheng Mao et al. On this. But these works, the first wave of results, were really interested in recovering exactly the unknown sigma star. And also what you can see at once from the first result I'm mentioning is that full recovery of sigma star is feasible only if the average degree in your graphs is order at least log n, so an order diverging with n, so you cannot deal with sparse graphs, okay? And so this motivated us to rephrase a bit the problem and attack the question in a different regime. This is the one I want to tell you about. Alpha is positive here, yes. No, they had explicit conditions. So they started off with alpha equals perhaps 32, and then they lowered it. And by now, as you will see, well, log n is good enough now. Alpha equals 1 has been achieved, but much more recently. But you'll see we'll be considering n times p of order 1 rather than polylogs. We'll get smaller. This means I can build an estimator from the two observations that succeeds. So it, with high probability, it returns the desired sigma star without any consideration of how costly it is to compute the estimator. And so typically you will have some regimes where you can produce estimators, but they take exponential time to be computed. Nevertheless, they exist. So it's information theoretically feasible, but computationally infeasible. And if you can construct your estimator in polynomial time, then it's computationally feasible. So we'll see some kind of gap. It's not fully understood. And this is one of the open questions that we do have on this problem. Yes. Okay, so what we will be considering is a regime that is a priori a bit harder than the ones where the average degree in the graphs goes to infinity. We'll assume the average degrees are order 1, so n times p for us will be this lambda thing, and this is going to be a constant. And we know from Kulina and Chiavage that there's no hope of recovering sigma star fully because we are below the if and only if threshold for that. So we relax our objective. We'll be happy if we can recover it partially. And by this, we mean we can produce some estimator sigma hat such that it agrees with sigma star on a fraction of vertices that is bounded away from 0. So formally, we define the overlap between two permutations as the fraction of indices on which they agree. And so we ask that this overlap, this fraction of vertices on which they agree, is bounded from below, away from 0. So at this stage, I wanted to ask you if everybody was happy with basic results on R-Shreni random graphs, or whether it was helpful to review some of the basic facts. And so if someone in the audience would like some background, I can spend a bit of time telling you about the seminal results of R-Shreni, about connectivity or emergence of a giant component. So is everyone very familiar with R-Shreni graphs or not? Probably not. Okay, so let me spend a bit of time telling you why R-Shreni are famous for their work on this, and then we'll return to our problems. So, okay. Switch decks. All right. So I'll go rather quickly, but at least this will give you a flavor of the field of random graph theory. So R-Shreni published two very influential papers, one in 59, one in 60. So it's not very recent, but still it's interesting. So the first one was about a phase transition in those R-Shreni random graphs. It was what they called the emergence of a giant component. So I'll tell you what this is. And then there's a second phase transition, which is the emergence of connectivity in those graphs. And so emergence is as you vary the parameter P, you increase it, you create more and more edges in those graphs. And suddenly for certain threshold values of P, some properties of the graph start to be met, whereas they were not met before when P was below the threshold. So let me tell you about their first best known result, which is the emergence of the giant component. We'll have lambda equal P times N describe the average degree in those graphs. And so this result states a phase transition as you vary lambda when it crosses the critical value 1, when the average degree in your random graph of Erdős-Rényi type is 1. So let me parse this. You can take your graph, identify which components are connected, so you can enumerate the connected components in the graph. And let me call C1 the size in number of nodes of the largest connected component, C2 the second largest, and so on and so forth. Okay, so the result is as follows. If lambda is less than 1, then with high probability, with probability going to 1, the largest connected component in this random graph has size log n times some constant, which depends on lambda. So all connected components are of size at most logarithmic. So the density, if you relate this number of vertices to the size of the graph, this is exactly going to 0. So all connected components relative sizes vanish to 0 as n goes to infinity. Now, if you let lambda cross this critical value of 1, that is when you see the emergence of what they called the giant component. And formally, the result is as follows. The size of the largest connected component C1 normalized by n will converge in probability to a constant that is strictly positive. And this constant is 1 minus px, where px is the extinction probability of a process that is extremely well studied, which is the Galton-Watson branching process. That's the extinction probability of the Galton-Watson branching process, where the offspring distribution of each individual is Poisson with parameter lambda. So I guess we are going back to 1959. We could go back to Galton-Watson. It would take us to 1873, but maybe I won't do that. And I'll assume you know about branching processes and extinction probability. Okay. So supercritical phase, we have a giant component. The largest connected component has size roughly 1 minus px. All the other connected components have size at most logarithmic. So one big component, many tiny components. So let me perhaps tell you in a few words how one goes about proving the first half. So it is established as follows. You would start from some vertices I naught, and then gradually construct the connected component of I naught. So you have a reservoir of n-1 vertices, and then you say initially my active set is just this I naught. And I'm going to construct the connected component of I naught gradually. So I will start by activating its neighbors that I have not revealed. Okay, and so that will be going to A1, which will be, okay, its neighbors here, set of neighbors. I think I denoted by D1 the nodes that are activated. And so the size of D1 that follows a binomial distribution with parameter n-1 and p. Okay, and I I'm going to kill this node. And I have a set of killed nodes, which is reduced to I node, and then a set of newly activated nodes, which is set D1. And I'm going to do that iteratively. I'm next going to pick another vertex here. So I'm going to kill it. I know it was a neighbor of I node, but it may have additional neighbors. So I'll have D2, which has a size D2, which is now binomial with parameter n minus 1 minus those guys I don't want to take into account. They are already accounted for. So that will be minus D1P. And then I can proceed like that. And I'm going to iteratively explore this connected components. So I have formally the following. I have 80. This is the number of active nodes at step T of my construction. DT is the number of newly added active nodes. And AT by construction is 1, the I node, the initial node, minus T, the number of killed nodes to get to step T. And then I have added D1 through to DT to get to step T. And this is what I was writing. I know the conditional distribution of how many nodes I'm adding at one step. This is binomial with the parameters P for the probability and N minus something for the number of trials in my binomial distribution. And so critically, if I carry on, at some point, I'm going to reach a situation where I have no active nodes anymore. And at this step, I will have constructed my whole connected component. So when I consider T the first time at which AT reaches 0, then I can use also the formula that AT, as I said, is going to be 1 minus T plus D1 plus dt. And so I know that T is going to be equal to 1 plus D1, etc. plus dt. So the time at which I hit 0 with my process is 1 plus the number of newly activated nodes. And so that is the size of the connected component. So in other words, to characterize the size of this connected component, I have to understand the heating time to 0 of some process, which is reasonably simple. It's almost a random walk, except that the distribution of the number of new things I'm adding when I move one step forward depends on what I have done before, but it depends only mildly on what I have done before. Okay, so this is this kind of construction, this relationship between construction of a connected component and a random walk that allows to prove the kinds of results for the emergence of the giant components. So let me proceed. So in terms of the random graph, yes?
Mathematically, complete this argument, you justify elementary arguments? Or
No, I think you can really follow this. This is essentially what there is to it. So the heating time to 0 of this process is distributed as the size of connected component in this random graph. So that's exact, and there's no catch. There's no subtlety hidden. No. No. It's first principles. And so to get the subcritical phase, what you would do then is to say, okay, my two processes, they make sense in terms of my random graphs only until I hit 0. After I hit 0, there's no meaning to those constructs, but nevertheless, I can continue them. I can continue the process arbitrarily in time. And so this is what I'm considering. I'm considering my process continued indefinitely in time. And now I'm going to say, okay, the probability that my size of a connected component is larger than K. This is the probability that I have not hit 0 by time K. I'm still above 0. Well, I'm going to upper bound this by the probability that I'm above 0 at time K. So this is, yes. Yes, it is lambda by n. We will do that. Yes, at this stage, I have not done it, but we will do that indeed. Yes, you're right. Okay, so I upper bound my tail distribution for the size of a connected component by this. Then I use Chernoff's inequality, and it turns out that I can upper bound my, okay, this I can upper bound by binomial of n and p. Okay, I'm just adding more trials, so I get larger random variables. When I do a Chernoff bound on a binomial distribution, it so happens that I get a loser bound by taking the Chernoff bound if I had a Poisson distribution with the same mean instead. So this I have an upper bound. I'm not yet claiming a convergence of the binomial distribution to the Poisson distribution, just an upper bound at this stage. And so I get that the probability that my, okay, I get this probability that C has size larger than K is upper bounded by e to the minus K h of 1. And h of 1 is going to be positive when lambda is less than 1 by my Chernoff bound. Okay, so now I'm ready to prove the first part of that theorem in the following manner. I'm going to say that the probability that there exists I in my vertex set such that its connected component I size larger than alpha log n is going to be less by the union bound than the sum over I n of the probability that gamma I is larger than alpha log n. And now I can use the upper bound, and this is less than n e to the minus h of 1 times alpha times log n. So that is n to the 1 minus h of 1 times alpha. So if I take alpha to be, so I want alpha h of 1 to be larger than 1 to have this exponent be negative. And so I just take alpha equals 1 over 2 over h of 1 or something like that. And I can conclude using reasonably simple arguments. So I'm going to tell you a little bit more, but not going as much into details. The other side of the first theorem is a bit more involved, but I'm just going to say a few words about it. So how does one show the existence of this giant component when you are above the critical threshold of lambda equal to 1? First off, that's what you were just alluding to. We know that a binomial distribution with parameters n and lambda over n for lambda fixed, as n goes to infinity, converges weakly to a Poisson distribution with parameter lambda. And so you can take this exploration process I was describing, and you can notice that at step t, I had dt, which was distributed like a binomial with a parameter n minus 1 minus d1 minus dt minus 1, and then lambda over n. And when this is order 1, then this converges to a Poisson random variable with parameter lambda. So in other words, my exploration has a set of numbers involved that converges weakly to a set of IID Poisson random variables. So in other words, yes? Yes. So I have n here. This is O of 1. Yes, and so the product is going to be lambda plus O of 1 over n. Yes, you're right. You do need the product to go to lambda. Okay, so what you get from that is that the neighborhood of a graph of a node in an Erdős-Chrony random graph looks, if you don't go too far away from that vertex, it looks like a branching process with a Poisson offspring distribution of parameter lambda. So that's one ingredient that is quite important. And then you need a bit more information about this distribution of the size of a connected component. So there's a bound. I don't intend you to parse it. It's not so straightforward. It's due to Richard Karp. What I'm giving you is the elements of the shortest proof I know about this result. So this proof has been laid out by Richard Karp in the 80s, I guess. And so this allows you to say the size of my connected component, C, for small sizes, its distribution converges to the distribution of the size of a branching process with offspring Poisson of lambda. So with if you take a set of values from 1 to A for large A, this is going to converge the mass that it puts in this interval to the extinction probability of the branching process. And then this lemma allows you to figure out that the mass it puts besides mass on small values has to be mass around n times 1 minus px. Okay, so I'm making it short. It's not so easy, but it works. And so this is how you get at the result. So I'll not detail that. I'll just mention the second result, the one they published in 60, before I go back to graph alignment. So what I've described so far, the emergence of the giant component, it entails that for fixed lambda, then you have a giant component which has size order n times 1 minus px. Px being strictly positive, this is strictly less than n, so we face graphs that are typically disconnected. We have one giant component and we have something else. So it's not a connected graph. So Erdős and Rennie then went on to figure out when does the graph become connected. And so you need the average degree to be large, but more precisely, they figured out that you need the average degree to be log n plus order 1. So if it's log n plus, say, some constant c, then they have this exact limiting result. The probability that the graph is connected converges to exponential minus e to the minus c. Okay, so I'll just mention quickly how one gets at this result. Okay, so that's just rephrasing. Well, that's less precise. In fact, if average degree minus log n diverges, then the graph is connected with high probability. If average degree minus log n diverges to minus infinity, then it's disconnected with high probability. So the proof strategy for this second result is as follows. You consider the isolated nodes, so nodes of degree 0 in your graph, and you show that asymptotically, as n goes to infinity, they have a Poisson distribution with parameter e to the minus c. So if you think about it, it's easy enough to estimate the average number of isolated degrees. So you have the probability that I is isolated this is equal to 1 minus p to the n minus 1. And so from this, we can figure out, so if p is log n plus c, you can figure out that it is going to be roughly of order e to the minus c over n. And so we know the times over. Okay. So we do a pause then. Yeah. Yeah, maybe I finish this part and then we'll return to the main. Okay. So okay, so it's easy enough to get an estimate, to get the asymptotic expression for the average number of isolated vertices. But you have more. You have the fact that this is asymptotically Poisson distributed. So it would follow directly from convergence of binomial distribution to Poisson distribution if the events node I is isolated, node J is isolated, were independent, because we would have a binomial distribution for the number of isolated vertices. However, you have some dependency between those events, because if a node is isolated, it makes it more likely that another node is isolated. So, but the correlation between these events is small, and so there's a bunch of techniques that has been developed in the study of random graphs under the name of Poisson approximation methods, and that are quite powerful and that allow you to establish convergence to Poisson distributions in those cases where you have weak correlations between events. So this is what happens here. We have Poisson distribution with parameter e to the minus c. The probability that there are no isolated vertices converges to the probability that a Poisson random variable with parameter e to the minus c equals 0. So this is e to the minus c. Hence, this that's the explanation for this weird formula of Erdős and Renyi. And then you have to work out that this is the leading factor for disconnection in these graphs, in this regime. In other words, the probability that there is a connected component of size that is neither, that is not 1 and that is not larger than n over 2 goes to 0. Okay, and so that's something that you do using the union bound, and I don't intend to spend much time on that, but that was just to give you a feel for the techniques that go into the study of random graphs in the classical questions started with Erdős and Renyi in the 50s and 60s. And in the second slot, I will return to graph alignment. Okay.
Thank you, Laurent. So now we'll have a short break and we will start at 10:30 for the second part of the lecture.